Welcome to the lecture series on electronic devices. So we are into the module 5 where we are learning the different fabrication steps in detail. So in the previous lecture we have seen rapid thermal processing followed by ion implantation and chemical vapor deposition. Okay. Are you all able to see the screen, right? Okay. Okay. So today's agenda will be the concept of photolithography, etching and metallization, right? Etching and metallization, like metallization, it is the last part of the fabrication, but photolithography and etching, they are intermediate parts where they will be repeated 2 to 3 times for different applications, like which IC we are developing. Right? So quickly let me go through what we have covered in the previous class. In rapid thermal process, we have seen that the temperature is attained very quickly. Right? How that is possible? It is possible by using a reflector with the gold plating, right? And we are using tungsten lamps where they are giving out IR radiations, infrared radiations. So due to multiple reflections, the temperature rises very quickly. So within 8 to 10 seconds, we may get the temperature up to 1000 degrees centigrade, right? So in order to save the time, we can go with this thermal process, rapid thermal process. And in the graph, it is telling that as soon as the temperature is reached, desired value is reached, like 1000 degrees centigrade, the process for the process that temperature should be maintained, right? And after the process is complete, the temperature can be allowed to come down, or it is called as cooling down, right? So the speciality here is just this part where the temperature is rising very fast within seconds, right? And other process like oxidation and diffusion, they will remain same, just for the quick response, for the quick rise in temperature, we may go with this process. Next was ion implantation, wherein we saw we have some ion source, right? And from that ion source, the ions they are projected through different adjustments or arrangements, right? And finally, what is the concept here? The ions, they should hit the wafer with a very high kinetic energy or with a very high speed, so that that wafer it can absorb the ions, right? So this is an alternative of diffusion, right? For diffusion, again, we require very high temperature, that is 800 degrees centigrade to 1000 degrees centigrade. But here, we are not worried about the temperature. Here, what is our necessity? The necessity is very high kinetic energy of the ions, right? So that is achieved by this arrangement, wherein in the arrangement we have scanners as well as beam accelerator. So those ions, they will be projected and incident on the wafer with a very high speed. Because of that high speed, right, the ions, they will be diffused inside the substrate or the semiconductor. Right? So this ion implantation, it is an alternative to very high temperature diffusion process. Then we saw chemical vapor deposition. So in chemical vapor deposition, what we have seen, the vapors will be inside the electric furnace, right? And there we saw two types. Basically, low pressure chemical vapor deposition, and one more was plasma enhanced chemical vapor deposition. So this diagram, it is telling about low pressure chemical vapor deposition, right? So what is the concept behind this chemical vapor deposition? Actually, when we go with the oxidation, right? some part of the silicon is being used for getting converted into SiO2, that is silicon dioxide, correct? So some part is lost there, right? Some silicon it is being consumed. So if you want to avoid that consumption of silicon, that is 0.44 times, then what we have to do, we have to supply the silicon externally, right? So that is done in this process which is called as chemical vapor deposition. So SiH4 it is being added with the oxygen, it is being added with the gas which is being inserted here, right? And this will react with the O2 to give us the silicon dioxide. So external silicon in the form of SiH4 is supplied so that the silicon present on the wafer should not be consumed. Okay, so to avoid that consumption, we are going with the silicon chemical vapor deposition technique. So this was the concept covered in the previous lecture. So coming to today's topic of photolithography, right? So in the steps of fabrication, you people have seen that the photoresist is applied, then a mask is used, and some UV radiations are being incident through the mask on the photoresist, right? So what happens there? That entire process itself is called as photolithography. Okay, so let me draw the things here so that it will be more clear to you. Say now, this is the semiconductor or say silicon substrate, right? So here we have the SiO2 layer on it, correct? This is SiO2 layer, and above that, what we do, we just take the photoresist. We just apply the photoresist, right? So this is photoresist. Say let me write it PR, photoresist. So what we do, we just use a mask, correct? So mask in the sense, mask is something like here at this part, right? I will shade it. Right? At this part, a shaded part, it is like closed. Okay, light cannot pass through this, right? And even I'll shade at this part also in this point. So if there are two types of masks actually, right? Positive and negative, right? So wherever the shaded part is there, there the UV radiations cannot pass through it, correct? And where the UV radiations can pass, where there is no shade, okay, this is like a mask, correct? So this mask, what is, I'll write M for mask. So what this mask will do, it will allow the UV radiations which are being incident, right, to fall on selected areas, not on the entire area. Okay. So what is happening? Say UV radiations will fall on this area, it will not fall on this area. Again, it will be falling on this area, right? Here it will not fall. Again, here it will fall. Correct. So I said you masks are of two types, right? Or even you can say photoresist are of two types. Okay, not mask. The photoresist they are of two type. One is positive and the other is negative. So what happens? See here the exposed regions, right? Here the this is exposed, right? This is exposed. So here we have exposed regions and non-exposed regions. So X mark indicates it is non-exposed region, means UV radiations are not being exposed at this part. So depending on which photoresist we have used, positive or negative, right? The exposed part it can be etched away or it becomes like weaker, right? So this I am shading, right? This shaded part it can become weaker or it can become soluble, or the other way, the other thing can happen like uh, here this part may remain as it is, but the the part which is not exposed to UV radiation, that can become soluble. Okay, so I said you there are two types of photoresist. It is positive photoresist and negative photoresist, right? So if you want to remove the exposed part, then it is called as positive photoresist. Or if you want to remove unexposed part or unexposed material, then it is called as negative resist. Negative resist. Okay, negative photoresist. So here it depends. Like so here I said this is the X indicates it is unexposed part, right? Now what I'll do, I'll try to remove this part only, right? Unexposed. So when I'm trying to remove unexposed part, it is negative photoresist. So this photoresist, I'm using it to be negative, right? So after this step, how the wafer will look like? The wafer will look like it will be having photoresist and silicon dioxide, right? Here a window will be created, correct? Again it will have photoresist and silicon dioxide. Again one more window will be created. Again it will have photoresist and silicon dioxide, right? So here this part and this part they can be etched away, right? I have shown the diagram after etching, means this window is created. Why this window is created? So that ion implantation can be done here, right? So this entire process it is called as photolithography. Are you following? Okay. So if you want to do reverse thing, say if you want to remove this part, the exposed part, then you have to use positive photoresist. Okay. So that is the difference between the positive photoresist and negative photoresist. So how it is being done? So here we have some arrangements for that UV radiations to fall on the wafer. Okay. So now I explained you the substrate and everything, right? When one very interesting thing here is, say I have drawn this, right? So here it is two windows are there, you can think, and here some gate will be there, right? After we complete the fabrication, we'll have source, gate, and we'll have drain, correct? What this indicates, source, gate and drain, what it is indicating? It is indicating that it is one transistor, one FET, one MOSFET or one JFET. Following, this is one FET or this is single transistor we are speaking about. And in that single transistor, right, we are doing these steps. What we are doing, we are opening the window by photoresist, we are applying the light, right, using the mask, correct, using the mask. So this is the mask, right? So what very interesting topic, what a very interesting thing is here, what is the size of this transistor, what is the length of this transistor which are used in the chips? Yesterday I had said you, see, if there is a chip in your mobile, say of 2 centimeters, 2 centimeter by 2 centimeter is the area of that, right? Just 2 centimeters, or you take 1 centimeter, okay, 1 centimeter by 1 centimeter. In this chip there will be millions of transistors. Millions means how many transistors? Maybe 1 lakh transistors or 10 lakh transistors, right? So let us take, there are 10 lakh transistors. 10 lakh transistors in just 1 centimeter chip area, right? So what may be the size of each transistor? The other day I had said you, the Samsung, it is working on 5 nanometer technology. What do you mean by 5 nanometer technology? Means it is playing with 5 nanometer transistors. Okay, 5 nanometer technology means what? It is having, or it is using 5 nanometer length transistor means what? You can assume, or how can you write 5 nanometers? It is 5 into 10 raised to minus 9 meters, correct? It is 5 into 10 raised to minus 9 meter. Can you assume 1 micrometer? Can you imagine 1 micrometer? Is 1 micrometer visible from our bare eyes? It's not visible. And we are going beyond micrometers. We are going to nanometers. Yes or no? We use microscope to see these micrometer or these microorganisms, right? Like bacteria and all. But we are not thinking actually, we are playing with transistors which are in nanometers. Okay, and in that very small nanometer, right? This is 5 nanometer, right? So you can imagine how the mask is like. Mask should have a hole, right? Mask should have hole at particular region and it should have some blocked region in some particular region. So it may be 1 nanometer, correct? So the entire transistor is 5 nanometers. So this may be 1 nanometer. This blocked part or the opened part, it may be 1 nanometer, right? So how minutely they are working on it? Only that part has to be exposed. Okay, it cannot happen like a chalta hai. It can the light cannot fall on this part where we are not willing to make the window for ion implantation. No, it is very precise. Accurately, it has to be done. Okay, so for that we have to use automated machines, and that automated machine should have zero error. Okay, practically it is very difficult, but almost it is done. Why? Because if a batch of chips are manufactured, right? Maybe 10 to 20 or 30%, maximum 30% of the chips may go waste. Okay, because of that minute errors. But at least we are achieving 60 or more than 70% of the chips are good, working fine for us, right? So how minutely they are working on that? So I was saying about photolithography, right? So for that photolithography, this arrangement is done. What is there in this? See, here you are seeing die or wafer. Okay, this is this round part. Okay, this round part, it is silicon wafer. Maybe you can imagine that it is like a CD. Okay, CD disc. And onto that wafer, there is very small chip. You are seeing that, right? And on that chip, I said how many transistors will be there? There will be say 10 lakh transistors. Okay, so 10 lakh transistors on a single chip, and this photolithography, right, it is being done on those individual transistors. Okay, on a chip there are 10 lakh transistors. If you are assuming 10 lakh transistors on a chip, on each transistor that photolithography process has to be done, right? So for that we are using these uh, lenses, reticle, right? These are the some instruments, right? This entire setup has some instruments. There is mirror, right? Then there is mercury arc light source. Then there is filter, illumination diffuser, alignment mark detector, right? In interferometer and reference mirror. Then we have XY stage and we have laser, right? So few of the namings are being done here, but actually the setup has a huge number of minute instruments with the help of which this entire photolithography will be done. Okay, So I said you there are two types of resist, for positive resist and negative resist. In positive resist, the exposed part will be becoming soluble or it can be removed, and in negative resist, unexposed part or material can be removed, right? And silicon wafers, they are covered with UV light sensitive organic materials, which are called as photoresist only. Okay, so what is photoresist? If somebody asks you, you have to say silicon wafers which are covered by UV light sensitive organic materials. They are also called as photo emulsion, okay, or also called as photoresist. And for etching, actually we will cover the etching part, but for etching few solutions are used. Okay, NaOH, which causes, depending on positive photoresist or negative photoresist, which causes the etching process to happen. That means which part has to be removed or etched away, that part will be removed by this solution. Okay, in etching also we have again different types, we'll come to that. But this photolithography, it should be done on each and every location of the transistor, which are very huge in number on a chip, right? Then we have some other components like mask aligners also, right? So refocusing and realignment uh, should be very critical stage here. Like, what do you mean by refocusing and realignment? Refocusing or realignment means what? See, I said you minutely we are working on the photolithography. 10, 10 on 10 lakh transistors, we are doing this photolithography, right? If there is some misalignment, right? If the chip has been tilted, then everything will be wasted. Why? Because the locations are being changed, right? So that minute realignment and refocusing, it is very important part in the photolithography, correct? And why actually it is very tedious task, right? But still we are working on it. Why we are working on it? Because if this scaling was not possible, if we would not have the 10 lakh transistors on a single chip, right? Then we would not have enjoyed our life with so tiny, so small electronic gadgets like we have a smartphone, right? If this technology was not there, then we would have carried mobiles of 5 kg or 10 kgs. Like earlier, in earlier days, we had computers which were situated, which was fixed in a room, right? A huge hall. Computer was fixed in a very huge hall. Why? Because transistor size was too high there. Right? So as size of transistor decreases, the power consumption also decreases and speed increases, right? Current, it has to flow from one point to the other point in a transistor, right? If the size of the transistor is in nanometers, that means current is flowing just for nanometers range. If the size of the transistor is in micrometer, then current has to travel a longer range, right? So the speed is decreasing as the size of the transistor is decreasing, and even the power consumption, it is also decreasing, right? How it is decreasing? Because we know P equals to I into V, correct? So low current and low voltage is possible for smaller devices, and if devices are huge, then we require high voltage and high current. Yes. So this photolithography, it is being carried out, and key parameter in photolithography, one of the key parameter is depth of focus. Okay, it is called as DOF, depth of focus. So actually there is one formula. Let me erase the things. For depth of focus, we have formula. What that depth of focus tells us is, depth of focus tells us the range of distances, okay, range of distances around the focal plane. So depth of focus, it tells us a range of distances around the focal plane where image quality is sharp. Means what? See, on a chip there will be hills and valleys. So as in our day-to-day life, we see hills and valleys, right? Hills and valleys, hills and valleys. So between the two hills or in a valley, there will be river flowing, right? In the same way, on the chip also, there will be hills and valleys of transistors and currents, right? So depth of focus, it is telling that how best we can see the quality of the image. How best we can see the quality image on the chip, right? And it is given by one formula, which is nothing but lambda divided by 2 times of n into a the whole square. Actually, how this formula has come, it is not given, but you can remember this formula for the exam point of view, right? And there is another one method, chemical mechanical polishing, where mm, planarizing process is done using the chemicals, right? So that is not a uh, important thing here, right? But I think you have followed what is photolithography. Yes, the basic concept, I think it is done, and we'll move to the next part, which is called as etching. So what is etching? Etching is nothing but removing the unwanted part from the chip, right? We have earlier we used to do it with the wet chemicals, okay, or liquid chemicals, right? It is called as wet chemicals or liquid chemicals. So dilute HF was used. I think it is hydro. So dilute HF was used to etch the SiO2 layers. This was done earlier, but there was some problem with the selectivity, right? What do you mean by selectivity? Selectivity means what? See here, we have the substrate, right? And say in this substrate, we have on this substrate we have silicon dioxide and photoresist, correct? And if you want to etch this part, you want to etch this part, right? Only this part we want to etch. So selectivity means what? Selectivity means what? Only this part has to be etched away, not the other part. Okay, so other part should not be affected by this etching. Say if you are etching this part and even side by side some other parts are also being etched, then it goes waste. Okay, so that is called as selectivity. So this uh, dilute HF, it is just a chemical liquid. It is just a chemical, right? So that had a good selectivity. Means what? Wherever you wanted the etching to be done, only that was done by the HF, right? But there was one problem with the wet etching, right? Wet type of chemical etching, there was one problem that it was isotropic. What do you mean by isotropic? So vertically and laterally, the etching happens very quickly. right? So very small devices, wherever we have two small devices, right, and there it causes a problem. The fast lateral and vertical etching. See, earlier wet etching was used. Why? Because the size of the transistor was not so small, right? But as we are advancing in technology, size of the transistor it is becoming smaller and smaller. So now it is not preferred. Why? Because this isotropic property of this dilute HF, it is affecting the where the size is too small. Okay, so we have to use dry etching. In dry etching, what happens? In dry etching, what happens is we used dry plasma based etching material, right? So dry plasma based etching material, that dry plasma based etching material, it is selective as well as it is anisotropic. Here what was the problem? It was selective, right? Where we wanted the etching, it was doing, but it was isotropic. But we want anisotropic and we want selective. Both the properties should be satisfied. So which is satisfied by plasma based dry etching materials. But this wet chemical processing, it is being done for cleaning the wafers. Okay, now also it is followed just to clean the wafers, but not for perfect etching. For perfect etching we use the dry etching, right? Plasma based etching, it is also called as reactive ion etching. It is called as reactive ion etching. Okay, why it is called so? Because uh, for etching we use gases such as chlorofluorocarbons, which will flow into the chamber. We have the some this is the chamber, right? So this is the chamber. So from here H gas, it is shown here. From here chlorofluorocarbon, it is being passed at low pressure, right? So what happens due to that? Because of that low pressure, right, the velocity of the light electrons, it increases, or the kinetic energy of the light electrons. And even you are seeing here plasma radicals and ions, right? Even the kinetic energy of this will increase, correct? And it will hit the wafer. We are having the wafer here, right? And you are seeing some shaded part is already present here, right? So this shaded part will not be affected. Only the non-shaded part, wherever we have, like this one and this one, right? These have to be etched away. So when these plasma radicals and ions, they hit the surface, right? Some, because of that very high kinetic energy, right, and very fast hitting of these plasma radicals and ions, the materials will get etched away. Okay, this comes under dry etching only. Are you following? So what we are doing, basically we are bombarding. You can understand this word better. Bombarding the plasma radicals and ions with very high kinetic energy. So because of that bombarding, uh, the uh, the things will get etched away, right? The unwanted materials, they will get etched away. And here we have potential difference also. Actually we have cathode and we have anode, right? The chamber is acting like anode, and we are giving some RF power supply for that, which is acting like a cathode, right? And because of potential difference also, the electrons, right, they hit with a very high speed, because there is huge difference in the voltage. Okay, even that is being done, and even the chlorofluorocarbons, they also increase the velocity or kinetic energy of the plasma radicals and ions. So this is how the etching is done. Dry etching is done nowadays, but earlier we had wet etching, right? In wet etching, what we had, a problem was with the isotropic nature of the that wet etching material, that is HF, right? But in dry etching we have anisotropic property and selectivity property. Both the properties are satisfied. Can I extend for 5 minutes? Quickly I'll cover metallization also. Or shall I continue in the next class? Next class, huh? Next class. Okay. Continue. Shall I continue or shall I cover it in the next class? Okay. No problem. I thought you people might have be bored for continuing continuous 3 hours seating of the class. Anyways, so here metallization means what? It comes almost at the end of the fabrication process, right? Say we have the uh, source. Okay, so we have the source, drain, and gate. Right. So here becomes the source, then here silicon dioxide followed by gate and drain. This will be the final product, right? But how this wire has come out, right? How this terminal has come out of this, and how the connections are being done, right? So this is a substrate or semiconductor. So application of metal on the semiconductor wherever it is required, that process is called as metallization. So how it is done? Metal films are generally deposited by physical vapor deposition technique called as evaporation. Okay, maybe gallium arsenide or the gold. Okay, that also can be used. So how it is being done? Metal films are deposited. Okay, so here metal films are deposited for the connection purpose. By which technique? Physical vapor deposition technique. Like which technique? It is called as evaporation, right? Or even there is one more technique called as sputtering. Yes, it is called as sputtering. Okay. So how sputtering can be done? Sputtering, like here the diagram is telling the aluminium, right? So here we have argon and we have aluminium. Okay. So So how sputtering is done? Sputtering of aluminium, it can be done by immersing the aluminium into argon plasma. Okay, so we have argon plasma, right? You are seeing here, and we are immersing the aluminium into the argon plasma. So what happens by that? Argon's ion, they bombard the aluminium and they physically dislodge the aluminum ions by momentum transfer. Means these argon, they just try to dislocate this aluminum. Okay, and many of the aluminum atoms ejected from the target deposit on the silicon wafers. So what is happening? This argon is being bombarded on the aluminum, so that aluminum, they just come out, right? They just come out and they just stick on the wafer. Where is the wafer? This is the, actually this is the wafer, correct? So what we are doing, finally what we are doing, we are bombarding the argon atoms, and because of that bombardment aluminums are coming outside, and where they are going, they are being uh, pasted on the silicon wafers, right? Where it is being pasted, only where it is required, okay, not throughout. I have drawn throughout the arrows, but it is pasted only where it is required, like on the gate, right, then on the source, and then on the drain. Okay, but nowadays we are uh, they are preferring the copper also, not the aluminum, right? Because of some minor changes in electrical properties, copper can also be deposited, but copper cannot be deposited with the sputtering technique. This technique is not valid for copper. Why? Because if we go with the sputtering technique for the copper, then what copper will do, you know, copper will not stick onto the wafer, it will get inside the wafer, okay, diffusion will happen. Copper will not come and sit on the surface, no, it will get inside, it will get inside the substrate, and then it will change its property only. So for that, what we have to do, intermediate before copper deposition, we have to coat the material, right? So some barrier should be present there, like I think I don't know what is that Ti, because I am not that much related to the chemistry. I think titanium, or I don't know exactly, right? So some barrier will be placed before copper metallization is done. Okay, like titanium barrier, it is being pasted first, and then copper is pasted, so that the copper cannot diffuse into the silicon, right? Followed? Did you follow how this is done? Okay, so finally what we have, again we are telling the entire story of fabrication, oxidizing, right, photoresist, then applying the mask, and mask A, it is written as mask A, but we are applying the mask, and ultraviolet rays are being incident, right? And then we will remove the exposed photoresist, that means etching is done, right? Then a window is created, implantation is done. Implantation means what? Again we are create doping, or it is like called as ion implantation, so that N type material can be deposited in P type material, or vice versa, right? Then what is done? uh, Sputtering, that means what, metallization is done, right? And then connections can be taken outside, right? So this is how the uh, top view of the chip looks like, or you can think, here the metallization is done, right, only on these regions where it is shaded black. Other things don't require the metallization, so here only the terminals can be taken out, like source, drain, gate, and substrate. Followed? Okay, so here we'll stop, and we'll continue in the next class.